Goswami from IIT Kanpur, which I had the pleasure of visiting when he had a very successful quantum computing back action conference there. He's the associate professor of chemistry, got his bachelor's in Jadavpur University in 1986, master's at IIT Kanpur, and PhD from Princeton in 1994. Before coming to Kanpur, he was at the faculty of TIFR in Mumbai. He did postdoctoral work in Harvard and Brookhaven. He is the Wellcome Trust Senior Researcher.
Thank you, Charlie. It's always so nice to be introduced by someone like Charles. And I'm very happy to be back to Dialbag. I think this is my third visit here. I'm giving a lecture for the third time also. So there are certain things which will be common. So I have tried to this time talk about one of the new things we are embarking on, which is more to do with the nanoparticular size materials, and research is slightly going towards that direction. But you have to bear with me a little because I'm also a little bit new in this area, learning. Although we wrote a book together, it was more of a literature search in that field. Now we have sort of started working in this area, and we are also trying to learn some of the new events and nuance in this area. With that, I would first say that, as Professor Bennett mentioned, it is not no work is possible without the students. So at the very beginning, I should thank my students who are involved, and fortunately IIT Kanpur provides one of the most important differences from TIFR. That was one of the main reasons for my move, was the body and the number of students that you can have. My colleagues, one currently sitting in the crowd, would immediately come to know how important that is, because in TIFR I only had 1 or 2 graduate students, whereas here I don't have any dearth of graduate students, as well as there are some wonderful undergraduates and master's students who really make the lab going in the proper direction. But on the same token, that professor knob is something which we discovered when I was at Princeton working as a PhD student. And I have told my students, the day that I touch that and get myself photographed, that's the last day of in the lab, and I will actually retire the next day. Because till date, if there is any problem which goes with the laser, it's me who takes off all the coats or whatever and then gets the laser back to action. So I do contribute still. So, without much of an issue, what I would like to do is that, okay, so the first thing which we are trying to look at is, I will enter the quantum aspect a little bit. First thing is, we are looking at confined systems. That is what makes quantum. When you scale down the dimension, go to confined systems, we are looking at quantum. And so one of the most important issues of quantum aspects is measurement, which all experimentalists are supposed to worry about at the most. And observing and measuring the quantum system unfortunately alters its state. And that perspective, to start with, is perhaps one of the most difficulties of quantum computing information and whatever we want to do with it. So anyway, we have to take that into consideration when we consider qubit. And so a qubit is nothing, as we all know, is a decomposition of the possible states. And the 2 possible states that we have are the pure states 0 and 1, as we call them typically. And however, whenever we measure them, we end up measuring either one of the 2 particular states where the system is supposed to be. And until and unless we measure them, we know that they can be in any of the possible states. And that is perhaps the main reason why we say quantum way of doing things is much more richer as compared to any classical scheme. Because we have the possibility of all other systems that we are looking in. And in some way, one of the things which Bennett mentioned is wonderful, because I keep on saying that in my class, is that it's a difference between real number and complex number. the two different systems that we look at simultaneously in electrical engineering, when we do work, we also say that, we look at the electromagnetic field, we are looking at both the real and imaginary parts at the same time. We are doing keeping the tab of everything together, and then finally looking at real numbers, because at the end of the day, measurements are all real. So Schrodinger and his philosophy of looking at dead and alive things is the main event of these quantum aspects. And in terms of chemistry or chemical reactions, the most important thing which we have come to know in the last century is the fact that the chemical reactions are the most important events, and the man behind this whole story got the Nobel Prize. Although he was not the only one, there were lots of others who had contributed, but he's the one who is credited to actually visualizing an event in chemical systems, which is the making and breaking of bonds in real time. So this is the basic issue that we have in chemistry, and as long as we know how to do this in real time, we are actually looking at quantum mechanical event in real time. And if we can do snapshots of these, a control of how these snapshots are going to come to us is perhaps what we are after when we are talking in terms of utilizing this into quantum world. That is one of our aspects, and that's why chemistry somehow becomes important in this area. Although this part of chemistry is so intimately mixed up with physics that very often, for just reference sake, I was in the physics department in TIFR, and so on and so forth. It basically is such a mixed up situation that most people who are in this particular part of the business are very difficultly indistinguishable. They are in fact the superposition states between physics and chemistry, if I would be allowed to say. Okay.
Excuse me, if you're, as a chemist, the previous picture, what's going on appears to be forming a hydroxyl radical and a free iodine atom, which is not what the words say.
Well, actually, I think what happened was this was taken out of the Scientific American, which came out, and the words were later on added, so it got mixed up. Okay, so the aspect of adiabatic quantum computing, which has been a more recent version of quantum computer, which is becoming more popular, is to see whether we can take the concepts of NMR quantum computing, which has become very popular, into other domains. One of the most important aspects of NMR quantum computing is that it utilizes the molecule as the computer. So the entire computation actually works on a given molecule, because it's addressing the protons in a given molecule and is having them interact, and that's how it's making the computer. So if we are going to bring this hugely successful process as of now into other techniques, we have to try to do it in this way. So one of the aspects which also has been used in NMR is to do things in a more adiabatic manner, so that the system is able to follow the process which is being attempted at it. And that's how the logical implementation of quantum gates use ground state spectral graphs and Hamiltonian language, and that is the way that we can use it in the other areas. So the final resulting quantum gates would represent a device that performs a unitary transformation on selected qubits in a fixed period of time. That is what we would like to have. The computational procedure in the adiabatic quantum computing model is therefore described by continuous time evolution of a time-dependent Hamiltonian with limited energetic resources, so that we are able to keep the system under control. And with this advantage which comes is, we can perhaps make situations where system is trying to go out of control, keep it under control always in this process. The problem in this process is also known. which is the fact that there is intramolecular vibrational redistribution, which has time scales which are much, much faster as compared to what happens in NMR. In NMR, the time scales are so slow that we in fact have to think of resetting the spins, whereas in case of optical or other spectroscopy, where we have similar issues, it is very, very fast. So for instance, if you have an excitation going to the vibration, they vibrate all right, but this vibration essentially immediately connects to all the other possible molecules, and therefore other possible atoms in the molecule, and therefore it's a overall vibrating system, and we wanted to keep it under this mode so that the control could have happened, which is now impossible when we have essentially excited all the possible modes. And that's why controlled chemical reactions are very difficult. If you would like to break a given particular bond, it's always the weakest part of the molecule which will break if this particular bond is not the weakest. And these time scales are much, much faster. That is one of the biggest problems. So some of the initial experiments, which dates back to the 80s, were more focused on trying to see if you can, I think you saw some of this atomic physics principles yesterday when they were trying to show in terms of quantum dots how these have been attempted, that theoretically and experimentally, when you do atomic physics, you can see Rabi oscillations, which are basically just two-level systems which are connected and coupled, and the oscillation will go, population can go back and forth. Ideally that should happen, but whenever you have other states associated with it, it doesn't work, and they don't show oscillations nicely. They just show an average which is having oscillations dampening away very fast. That's one thing. And the other thing is, on an average, since you cannot resolve these, and there are many of them coming at different delays because of systems having different frequencies, they are not exactly resonant at the same frequency, you end up seeing a washing away of the oscillations. So ideally, if you would like to go completely to the excited state, which is possible to do theoretically by coming up with pulses of light, but it is very difficult to do it by just simply using a short enough pulse of light, which is resonant at a given frequency. One of the ways it could be done was to use the principle of adiabaticity, where you would make the system believe that it is going to evolve as per the applied field. So that what you do is you basically move the system in a slow enough manner so that the decay or the dephasing of the system is not coming into the picture. And that is one of the ideas which is used in terms of adiabatic population transfer, and thereon you can show that you can in fact see a 1:2, because this will roughly average out to be 50%, and if you can take advantage of the fact that you are able to move the system adiabatically, then you will be able to go 2 times of what the population transfer otherwise would be. So this is a model of how it sort of works out. You can see that if you think it's a simple 2-level system, you would like to keep everything here, which we know didn't work. As we saw earlier, all the populations got transferred into the different vibrating modes, and you can look at it in either way. It is as if the second level is not pure, it's distributed between other states. So that is one way of looking at it. The strength is distributed, or you can say that you have excited and that slowly goes away, as I was trying to show you. If this happens in very short time, femtoseconds, you can never see it, and in fact, so these 2 particular ways of looking at it is essentially identical. And this has been shown in reality in experiments by, again, one of the early groups which showed it was Zuel and Felker. Both Felker is also a professor now in UCLA, where they had used as an anthracene molecular system in molecular beam, where the temperatures could be brought down to situations where only couplings between well-known states could be excited, and they were able to see these beautiful oscillations which were otherwise not possible to see as you raise the temperatures, and they were able to see how these oscillations were getting damped or how they were getting connected by using these kinds of short pulse spectroscopy. So one of the ways you want to actually then work in these timescales is to use a short pulse laser pulse. The advantage of a short laser pulse, as you can see, is that it is better and better in time, so it has a very high, it can do things before the dephasing of the system. But on the other hand, your resolution in frequency goes worse and worse because your bandwidth is becoming larger and larger, and so no number of excitations that you will be actually addressing, or in other words, if you go into this picture where the number of states which will get affected will become larger and larger because the bandwidth of the spectral part is larger. So you have to worry about that. That is one aspect. And that essentially the other high resolution spectroscopies therefore always try to use the CW or the continuous wave lasers where you could go down to the simplest, the best possible line width so that they could try to look at one single spectral line. So the two aspects are very different. The longest period of time that you can take information from a system with very little perturbation gives you information of a given state with the highest level of accuracy. Whereas on the other hand, if you are trying to get information from the system at the shortest possible time so that other instances of coupling do not occur, then you are confronted with looking at too many states at the same time. So essentially, whichever way you go, you cannot beat the system. It has, in both the cases, loopholes built in for you. Okay, so you have to come up with ways of doing things which are a little bit more sophisticated than just by looking at the laser pulses or doing things like that. So one of the techniques is to basically change the light properties so that you take advantage of both the techniques. So one of the ideas is to change the property of the wavelength within the laser pulse so that the laser pulse itself, the property of the laser pulse is changed so that the phase condition or the content of the wavelength within the laser pulse is also being connected in such a way so that the system will not, so it becomes a coupled system in some case. The best possible use of this technique of late has been found to the fact that if you can do this fast enough, or you can actually connect it to a computer, then you look at the result, and once you are starting to look at the result, you feed it back to the system, because the computer is the one which is feeding to D, which is going to modulate the pulse. So you can do this iteratively so that the results that you are looking for, unless and until that comes, you keep on closing the loop. So this is known as a closed loop control process, where until and unless the control parameters that you are looking for does not arise, you keep on sending it back to the computer or sending it back to the light pulse saying that I want this property to change, and so on and so forth. So this particular closed loop pulse shaping technique has given rise to certain control processes which are otherwise very difficult to understand. Now, by looking at these controlled events, people are also trying to understand whether they can now tell something about the molecular event that happened. Unfortunately, it turns out that the approximations often grossly point out very simple results, whereas when you use those approximated simple results to get back the response that you had generated, it somehow doesn't work. So although we have very simple results that can be generalized by doing very small little approximations, those small little approximations seem to play a major role in controlling the process. So this is the control community now is bifurcated into many piecewise groups. One community thinks that it is actively modulating the system, so it's a driven oscillator problem. You basically drive the system thinking in terms of a spring which you are basically driving to a point that it has no say anymore, and you are able to get the answer out of it. So that is one of the principles where it is known as adiabatic picture also, because you are basically driving it to a point that it just keeps on going with the field. That is one approach. The other approach is they are saying when we do it in this fashion, when we are able to control it by just doing small little iterative changes and finally we get to an answer that we liked, that means the system is able or amenable to control based on the fact that the small little iterations were good enough to bring it to the solution that we wanted. Unfortunately, in this category, when you try to get back to the solution by making small little assumptions such that you will only need, let's say, a linearly changing phase that is good enough to get to a certain solution, although a very small amount of quadratic phase was there. Under the approximations, the quadratic phase factor is, let's say, 1:100. So you can always say, I can ignore that. Unfortunately, that 1/100th of the quadratic phase was enough to get to the final solution. If you ignore that, you don't get the final solution. So another part of the community is saying that it is that 1/100th of the event which is most important. So there is a lot of issues which are associated with this field, but in general the technology has now evolved to a point that it is possible to close the loop and you are able to look at events which you can do with it. So that is one part of the story. What I wanted to show you here was if you still preserve or look at the principle of the way we are looking at it, since we have defined in terms of quantum computing language that we have now accepted, is that we have a two-level system which we define as a qubit, and we are saying that whatever problems we are facing is because of the fact that the two-level system approximation is getting corrupted as a result of many other events which is happening. So at the end of the day, we would just want to know what is the two-level character of a system and how can we come to terms with this two-level character and how can we sort of reduce the other effects on it so that we can do the computation the way we want it to. Let us not get perturbed too much by the other events. So that is one approach to this whole problem. So in this particular approach, what we can say is that the simplified system essentially is just a two-level system which is now amenable to control. Now you can write down the Hamiltonian for a two-level system very easily, and if you have those kinds of complex pulses, you can apply all kinds of field properties that you would like to. You can even think in terms of that you are not going to use only one photon field because that might be restrictive. You can have many photons coming and interacting. You are just trying to build in more and more control parameters. Typically, linear systems are most difficult to control or least robust in terms of control. You will get perhaps one solution, but any difference in the process, and since these processes, as we know that even a very small perturbation takes it away from what you are looking for, that's why nonlinear way of looking at the problem is always supposed to be much better. So people are always interested in nonlinear events or trying to take a system into a nonlinear domain. So nonlinear way of looking at the problem is what we always do, and the frequency and its relation within the pulse, which is the phase, is the most easy to control, and that is the one which is often used. So here are certain graphs which is trying to establish that how the two-level system is interacting with an applied field, and so you can start seeing, you will be seeing Rabi oscillations for a simple two-level system, and how the off-diagonal elements, which is basically the coherence property of the system, how it evolves under different amounts of applied field that you can look at. You can understand adiabaticity more in this picture. It's a simple concept of applying the field and getting it to go in a given direction. I don't need to discuss more on this here. The main issue to understand is how much of a field intensity that you would be needing, that is one aspect, to get to adiabatic situation, and that you can say very easily and very quickly by looking at the off-diagonal elements. That is one way. The other interesting thing or feature to look at is that when you are looking at it in a situation where there is adiabatic principles being in operation versus when you are not applying any adiabatic principle, which is the pi pulses, the area of the pulse only, the two operations are different. And that is well understood because when you are using the adiabatic principle or the situation of driven oscillator, then you are actually addressing the system through the coherence terms. Whereas when you are using the area under the field approximation, then you are using the dipole field. That means it is only the connectivity of the states which matter. So in the two cases, one is sort of like connecting it. I will come in a little bit more detail here. In fact, I'll just skip all this and go straight to this. These are too many issues here. I will just go, wait, yeah. So what we are interested in, so this is something which you can do theoretically without even bothering of looking at the experiments. And to understand what you can come to is to get to the understanding that when you are looking at, so generally all the absorptions are composed of both the real part and the imaginary part. The real part is the dispersive part, the imaginary part is the absorption part. When you are connected by a dipole coupling, then you are actually accessing the imaginary part of the problem. When you are using adiabatic principle, then you are actually using the real part of the system, which is the dispersive path. And that's why when you cheat the system to sort of go through the driven oscillator part, you don't even access the imaginary part of the system at all. And so howsoever highly it might have been coupled, which would have caused the absorption, all that, it does not matter anymore. Okay, and that is one of the advantages of using adiabatic processes versus the Rabi flopping process, because in the Rabi flopping process you can never achieve a 100% scenario that you will not see any flopping. You will always see a flopping if you are using the area principle where everything is connected through the imaginary part. So these are certain of the things which we found out. And the other important aspect of this exercise that we saw is that we could quantify how a two-level character of a system came out in 2007. How the two-level character of a system is getting corrupted by having more and more of states which can be coupled to it. Okay. Okay. Now, what do these measurements and implications of coherence have importance to us? One of the important aspects of it is the off-diagonal peaks that we can get. Now, in terms of NMR, we have an analog, which is the 2D Fourier transform spectroscopy, which occurs in the infrared region. And we can do that in the infrared, and we can actually measure optically the through spectral interferometry with respect to known signals. And people have already done that. In the simplest case of rubidium, for example, which is a perfect two-level system, rubidium atom, you can see how the excitations are coupled. So you are looking at the coherence between the two states. Rubidium, like you have seen the sodium lamps. See, the yellow color there that you see is because of the D1, D2 lines. There are two lines, atomic lines, and because of that you see the lamp, the color. And similarly in rubidium, it's at an infrared, near infrared region. And it so turns out that near infrared region is accessible commercially through a titanium sapphire laser. That's why it has become a so popular scheme to be used. And all the cold atom trapping, all those experiments are based on rubidium systems. So rubidium turns out to be a quite interesting system. Rubidium also is one of the systems which is quite interesting because it enhances the spin, it allows the spin connectivity to xenon and other molecules, and so it has been shown that if you have a way to enhance the coupling between them, you can see, you can have rare gases mixed up with the regular gas, which you can then breathe in and get a better lung imaging and other kinds of things. So people have done all kinds of applications of this scheme. But generally speaking, the most important aspect of rubidium is that the wavelength region of access is resonant with titanium sapphire laser. So the two-level problem of that has been looked at. And the implication of the measurement for 2-photon absorptions, let us see some of the experimental results here. So, So for the robust temporal control, therefore, we have the first criteria of nonlinearity, and the simplest one is the simplest two levels is nonlinearity. Two photon nonlinearity is the simplest one. So we have done some work in that area. One of the ideas was to look at molecular design of systems. So we have some organic friends. Well, we don't know how to make molecules. That's unfortunate, but that's how it is. But they have given us all kinds of molecules which we looked at, and we saw that in fact it is indeed possible to look at enhance the two photon character of molecules, so they become very useful dyes, and they can be used for and they can also be used as switches. For example, in one of the particular cases we found that metal substitution on a ligand, these ligands are drugs that you typically use. Porphyrins are ones which are also found in our body. But if you have a metal substitution on that, it becomes highly nonlinear optic. I mean, it has a very high two photon cross sections, whereas the other one doesn't have any two photon cross sections. So you can actually look at metal chelation, for instance. You know, nowadays there is a big drive to see whether heavy metals are actually absent in the drinking water or not. It's very important to remove heavy metal. So one of the ways that is actually done is that these molecules are added so that the heavy metals get absorbed and then they are removed. So one of the ways to see that your removal has been done properly, the metal chelation has been done properly, is to see the nonlinear activity, for instance, of these kinds of molecules. So there is a lot of drive to understand how these kinds of work. We also tried to look at what happens when the frequency content within the pulse is changed, and we tried the simplest case where the frequency was changing linearly. It turned out that it's actually not a very simple solution. It's not that you will be showing that across a certain point the two photon cross section is increasing or not increasing. It went through a lot of changes, and also it depends, very highly depends on the system of choice. We later on found out the reason why it is, but initially we were very surprised and were struggling to understand. It turns out that with all these phenomena that we see, there is the most important thing we have to worry about, as yesterday's slides were also showing, that when we are looking at short time scales, we often are not worried what happens at very long time scales. And so in some of the pump probe data that you saw yesterday, there were some, before zero, there were oscillations and things like that which was happening. That is because, as she was explaining later, that the event, that there was a long time event which was not getting over by the time you were looking at it. And that's typically known as a pile-up error. A pulse pile-up, in the sense that one pulse effect is not gone when the second pulse is coming. Although on the short time scale, almost the entire event is over. Turns out that thermal processes are very nasty in this way. And thermal processes last seconds. Often they can run until seconds. And these thermal processes, unfortunately, are so small to start with that you will not be able to detect the effect of a single pulse thermal effect until and unless all these thermal effects, let's say after 1,000 shots, have piled up and have completely corrupted the measurements that you are looking at. And most of the problem is that when you are making measurements, in order to make something which is of any use or having some level of signal to noise, you do make measurements which are on the order of 100 to 1,000. And that's why you often get into these kinds of problems. So these are all practicalities of experiments that happen. Here is a little bit of a twist into the biological side. What we also found that when we use these two photon processes, it's a very useful way of looking at malignancy versus normal specimen. And these was done, this is a complete piece of work. This has been compressed to one slide here. Please excuse me for that. What we had done was we looked at a simple microscope results, slides of patients having cancer, and then compared to normal patients, and they had only a little bit of suspicion in through the microscopy, simple microscopy technique. They could not really pin it down. However, when we did our two photon process studies, we could really pin it down with an efficacy of more than 98%. So that is much, much higher. Their efficiency was about 60%, by using a normal microscope, whereas when we actually go to a 2-photon process, we can go up to 98% accuracy. So these do have other implications, and that's why Wellcome Trust also supports us. But generally speaking, the overall picture until now, what I have tried to show you, I have not yet actually entered what I wanted to do. So I'll now conclude what I was trying to tell you all about, is mostly that we have looked at molecular systems and processes and their nonlinearities, and have also tried to see how we can control, how much of a control we can do, and tried to see if there are any two-level system, how much of a two-level property that we can look at. And based on that, we have actually tried to do molecular understanding in terms of time scales. We looked at different time scales of processes. We are interested in interfaces, because interface turns out to be a very important study. All of those who do quantum dots and nanomaterials, they know that interfaces are extremely important. So we do pump probe studies of interfaces, and we have done multiphoton imaging as well as optical tweezer. That's the one which I'll talk about now a little bit more. And the other interesting thing that we have just finished and we have managed to show is that you can also do single photon imaging by using a pulse light much more effectively than you can do by continuous wave light, because it turns out that short pulses, in fact, also mean, the shorter the pulses is that they also exist only over a certain period of distance in space. And that's how you can get actual resolution in terms of going up and down, and you can utilize that for a microscopy application. We have also done some of the infrared spectroscopy of 2D imaging and things. Okay, now, most important thing, therefore, is first to look at how to design. Now, we had already looked at a molecular design, and I admitted, hands up, we don't know how to do that. What we know is something more. First, let's try to understand one of the design processes, which is, let's look at the simplest of all the possible designs is trying to do a bottom to top up kind of a thing. There are two ways of doing it. One is to go from top down approach, which is sculpture, for instance. Okay, so if you take, you know how these big sculptures are done. You have a piece and you curve away and you get the sculpture done. The other aspect is to try to put together things and build a building. For instance, you use bricks to build up a building. In order to do that, you have to first understand what kind of a potentials to be utilized. And the most often used is the Leonard-Jones potential, which has both an attractive as well as a repulsive term. And that's the reason why you have a net interaction which is stable at a certain point of time, certain distance. And we thought that we will look at one of the possible cases of looking at nanoassembly, which is self-assembly often, which has been used. And the question which often comes around is, why do you get cavities? And in crystals, it's also known that there are defects. And it's generally known as a natural phenomenon. First thing is to see why it will be like that. Even if you take the ultimate situation of a square, which you know if you can put together in a way, there is no possible way of seeing any gaps. If you allow it to evolve in the way that a potential of that is supposed to go ahead, you will still see cavities and defects in it. How does that happen? In general, however, molecules are often taken up as circles. So what we did is that we took a large number of them, and they were randomly spaced. They were spaced randomly with respect to position and angle, and the square curves of each were with the number of, it's a large number were taken. The central square in the canvas was taken as the seed point. And so we started it to evolve, and we started this evolution to work. This is a numerical simulation. At an intermediate point of simulation, when the seed is grown and essentially speeds up the process. This actually starts speeding up, because as the size grows, its attraction goes up. So one of the things to notice, however, here is that as it is coming, there are situations when they will touch, and then it has to orient itself. It can go around. And in all the possible cases, we are trying to make sure that there is a minimum possible gap which is available. And the idea is that if you let it go for a very long time, so this is a simulation result which is after a month or so, with lots and lots of squares which are put together. you will find that it actually does go to the circular point that you would like to have. This is the simplest model of two-dimensional. So it's just a square, and if you go into three-dimensional, it will be a cube and a sphere. And here you would get to the point. So we came to know that our simulation was in the right direction, because you would get to this minimum surface area. This is the minimum surface area was our constraint. And so we knew that what was expected is true, that even if you apply all the constraints and everything, no matter what happens, you do end up getting defects. That's one of the very interesting results out of this. And secondly, the other result which was very encouraging is that if we design so that in fact it's only two sides are active and the other two sides are not active, you can actually go ahead and do a coded design. In other words, you can then get lines and things like that, rods and things like that, because you are actually allowing the code to work through. So this is one of the simplest way of looking at nano design in some sense of doing nano things. It's interesting. I thought that, you know, this kind of a simulation might have been done many, many times by many, many people and groups, but turned out that the undergrad who was doing this, he was the first one to have done this kind of a simple coding kind of a thing. So we didn't have any benchmark or any other place to compare it to. It turned out to be a very interesting result in its own. Okay. So the next thing which is of importance is not only to be able to design it or to understand how it happens, but also to be able to apply certain kind of spatial control. Now, the control over 3D motion is something which is which has been attempted in many, many ways. One of the ways is to use lithographic techniques, STM techniques. The other approach is to use light to do that work for you, and that is optical tweezers. And the other one is the control over molecular dynamics, which we have already looked at, which is the temporal control. Now, in order to get to the quantum computing or quantum information logic, I think you cannot just live with one or the two. You have to have what we now want to say as a spatio-temporal control. Unless you have a spatio-temporal control, quantum computing or quantum information transfer is not going to happen. And what most of us until now have been doing is we have been focusing, well, spatial control was essentially focused on by in a different field altogether. Mostly we have been focusing on temporal control, because we have been trying to say intramolecular vibration, all kinds of dynamics is very important. We have been focusing only on that. Turns out that both of them together is very, very important. So here is one of the things about spatial control. This is where we are trying to show how we can hold on to a molecule. This was made by one of my students in one of his presentations. He had this very cute picture. So it happens to be because of one of Mark Twain's famous statement, which he also has put together. But anyway, I mean, optical tweezers have been used for looking at and holding DNA and other work, and this is the statement which prompted that cartoon. I know a man who grabbed a cat by the tail and learned 40% more about cats than man who didn't. And so he put up that picture showing that, you know, if you hold a molecule, you'll know much more than whether if you don't hold them. Trap and twist single molecules. That is one of the dreams, essentially, if you can actually trap a single molecule. It has not yet been that way done. I mean, if you consider neurons, even neurons have not been really held by optical field yet. So mechanical tweezers first dates back to Louis Pasteur in 1849, who separated the DL and L forms of the sodium ammonium tartrate. And 1609, sun exerts radiation pressure. So basically that was one of the first ideas that came into the mind, that you can use a photon flux principle to use this. 1873 and 1917, again, they had the same idea that light does exert pressure, and it was finally Arthur Raskin and Stephen Chu in 1986 who showed that optical trapping, followed by who were able to show it in this Bell Labs. So, there have been lots of instances now about trapping. Now the most important, I mean the most sophisticated one of them is the trapping and cooling of atoms, which is going back all the way to 1997. It has already been credited with Nobel Prize, and the Bose-Einstein condensate as a result of that. Those are the high ends of this. Force measurements on single molecules have been happening over live cells, and this has been came out in Science in 2005 when they were able to look at almost a single molecular level live cell imaging. That's the neuron cell which they had looked at. And there have been labs around the world who do this kind of work. Okay. Now, how does the optical trap work? So, simplest one is to use the principle of the levitation trap, where you can just use radiation to sort of balance your gravitational force, and this is a typical case of an atomic trap where you can use these kinds of things. In case of the tweezer case, you have a little bit more to worry about, because you have to also take care of the Brownian motion which occurs in solutions. So, in that case what you have, you basically take advantage of the Gaussian beam profile which goes through the particle, and there is this bending of the base, and you can sit down and look at the forces which work on them, and you will find that, you will find that the restoration force, by using a simple principle of the spring, you can show that the restoration force is the one, actually I will show you. So, the gradient of the scattering and the restoration force can be used by using a simple spring mass system harmonic oscillator model to come to this principle of understanding how the trap works. Okay. And the trap is generally defined in terms of the stiffness of the trap that you have because of this. So, we have also built a trap, but the difference between the trap that is typically used is that we have actually put together a pulsed laser trap. Now, there is an interesting issue to worry about pulsed laser trap. Pulsed laser traps are ones where you have to be very careful about the time between the pulses. If the pulses are off for a very long period, then the trap doesn't work, because you need to have the immediate pulse coming so that the effect of the earlier pulse is not gone. So, this is actually a different way of the problem. Here again, we would like to have the effect of the last pulse be existent when we have the second pulse coming. So, in one case, when we look at dynamics, it is to our advantage that we can go to a gap between the pulses so that the effect of the first pulse is completely non-existent when we go to the next pulse. Whereas in this case, we want the effect of the first pulse to be there so that the pulse, the system does not get a chance to go away from the trap in the first place. So, obviously these traps don't work when you don't use oscillators. Amplified lasers cannot do a trapping like this. This particular kind of trapping does not work with amplified lasers, which are at a much lower repetition rate. So, the advantage of a pulse trap obviously is that you can do a 2-photon process while you are actually looking at a trap. So, that has a better advantage of looking at it. So, these are the few tiny things. One is that it actually has, because the peak power of a pulse can be much higher, you can beat the thermal process once again when you are having a continuous light coming, and in fact we have gone down to 100 nanometer size already, showing that we can do much better by using a pulse laser versus when you use, because in terms of 100 nanometer is actually a very difficult size to hold by using traditional traps with continuous lasers, because the thermal load on the system is so high that it often goes off of the system and it's not very easy to hold it. Whereas in this case, you can actually do an intrinsic, and you can show that very easily by using fluorescence of the system. So, we would like to go into further directions in this. I hate these kinds of, when they're very good, but sometimes they put in a lot of animations. So anyway, so when you go one step further, we would like to actually see trapping of particles of any size, difficulty in trapping single molecules, which will perhaps become a much easier way of looking at it, because our way of allows us direct visualization, and you can have high efficiency photon counters. We can look at molecules in the moderately intense fields, and obviously the biggest advantage here is that we can simultaneously do dynamics while we have trapped a system. So that is one of the, so spatio-temporal trapping or spatio-temporal dynamics is something which we are after. The control with trapped system is something which we are after. And here, okay, so I'll just give you one final experimental result on how you look at molecular fragmentation in a beam chamber. So here again we have, this is in gas phase. Okay, at the end also. In gas phase, this is a fragmentation mechanism of a N-propyl benzene molecule. Just using a blast of a laser light, you can just break them apart. But what you can do is, you can break them apart in different ways based on the laser power and capability. Most often what happens is all of them are formed, because if you are using your laser as a large hedge hammer, it will just break up in different ways. Now, when you use it in a molecular beam chamber and you sort of change the property of the light, so here again we actually use just a simple frequency modulated laser pulse. These are details of how you do the, so you can enhance the ratio of these fragments by using the chirp of the light, frequency content of the light. And so here are certain raw data which is showing that. It's difficult to see here. So what we can show that is that the certain fragments which are otherwise not enhanced or have equal distribution when you are using a regular pulse of radiation, certainly will get enhanced when you have the frequency of the light within the pulse changing. And so here is a situation where certain pulse frequency content will actually enhance certain things. So it is one of the another ways of looking at how you can control how the molecular channels are being looked at. So all this work is not possible unless you have the enough of a technology. So we have amplified laser technology which can give us about 1 millijoule per pulse at about 40 femtoseconds, which is at a low rep rate of about 1000 hertz. The other one is a homemade oscillator which can run at very high repetition rate. We have all these microscopes and tweezers which again are used at high rep rates. They are in close to 100 megahertz, 10 to the power 8 pulses per second. Then we have a pulse shaper which actually changes the pulse. And here is the final setup where, by the way, these machine is made with the help of turbomolecular pumps, which are nothing but your jet engine turbines that you use in the aeroplanes. And what we are trying to do, this is our slide of all the different things that can happen in a laser lab with when you have put together all the lasers, is that you can go between different phases of systems, so liquid, solids, gases. You can actually look at dynamics, you can actually look at spatial aspects, as well as you can do microscopy. All the different things can be done at different cases, and you can do entangled photon. We do have entangled photons, and we are trying to actually do microscopy with it, because we hope to see a lot more information than you can ever get out of a regular light microscope that we do as of now. With that, I don't know how what the future lies for us, whether it will be more of philosophy or more of science. I think nobody knows about it more. I found an interesting Dilbert cartoon which says, I have invented a quantum computer capable of interacting with matter from other universe to solve complex equations. According to chaos theory, your tiny change to another universe will shift its destiny, possibly killing every inhabitant. And you know how Dilbert goes. He says, shift happens, fire it up. So I don't know if we can say that, but that's how it is. Yesterday, I think we saw a slide which showed that 5,000 people, 50,000 people are, if 50,000 people are killed every year, whether you will go for that technology or not. And that was just a car versus a nano. So we don't know what lies ahead of us, philosophy or science or good benefit for the world. These are all the people responsible, some of the people actually, responsible for it. And Vishal has helped us write this book. Thank you very much. And we have the quantum computing, which Bennett was saying, has become quite a bit of a back action book, has become quite a bit of a success. I would recommend, actually this is one of the suggestions which I wanted to give Vishal about, that we do take out some proceedings with, because AIP, for example, is very, very interested. We can talk to Springer also. One of these which you can later on discuss. And there has been one book on lasers on chemistry where we had written something for most of the recent things, because I think lasers and chemistry generally do not gel, but it has come to a point people are beginning to let us be there, live there. That's how it is. Thank you.